This video is going to be the first one in our probability section, section 3.1, terminology. So by the end of this chapter, you should be able to understand and use the terminology of probability, determine whether two events are mutually exclusive and whether two events are independent, calculate probabilities using the addition rules and multiplication rules, construct and interpret contingency tables, construct and interpret Venn diagrams, and construct and interpret tree diagrams. So probability deals with the chance of an event occurring, measured by the ratio of the favorable cases to the whole number of cases possible. Probability is usually expressed as a number between 0 and 1. An experiment is a planned operation carried out under controlled conditions. If the result is not predetermined, then the experiment is said to be a chance experiment. Flipping a fair coin twice is an example of an experiment. And an outcome is the result of an experiment. The sample space of an experiment is the set of all possible outcomes. And we use the uppercase letter S to denote our sample space. An event is a set of outcomes of a probability experiment, and a simple event is an event with only one outcome. So an example, flipping one fair coin twice is an experiment. The outcomes are H equals heads and T equals tails. Our sample space is S equals H comma T, so it's a list of what the possible outcomes are for our sample space. One possible event could be the event A, getting at most one head. There's lots of different possible events that you could have for that, or for any experiment, but this is just one. And the probability of an event A is written as P parentheses A. So probability of event A. So the probability of any outcome is the long-term relative frequency of that outcome and is between 0 and 1. So we've talked about relative frequency before. So that's how many times it can happen divided by the total number of possibilities, and that's probability. So P of A equals 0. That means that the event A can never happen. P of A equals 1 means the event A always happens. P of A equals 0.5 means the event A is equally likely to occur or not occur. Equally likely events are ones that have the same probability of occurring. So if it's 0.5, the options are occurs or does not occur, but you can have other situations where you have equally likely events that have a lower probability than 0.5. Examples: if you toss a fair six-sided die, each face, the faces on a die tend to be 1, 2, 3, 4, 5, or 6. Each one of those is as likely to occur as any other face, as long as it's fair so that it's weighted the same. And so you get, each side has an equally likely chance of showing up. If you toss a fair coin, head H and a tail T are equally likely to occur. And if you randomly guess the answer to a true-false question on an exam, you are equally likely to select a correct answer or an incorrect answer. So those are examples of equally likely events. Processes such as flipping a coin, rolling a die, or drawing a card from a deck are called probability experiments. A trial means flipping a coin once or rolling one die once, things like that. Possible outcomes. So flipping a coin has 2 possible outcomes. The roll of a single die has 6 possible outcomes, etc. Theoretical probability is a fraction or decimal. So remember, probability is between 0 and 1, but you can express it either as a fraction or a decimal. And is equal to the number of desired results in the sample space divided by the total possible outcomes in the sample space. Again, that's back to the idea of it's the relative frequency of the event occurring. So here are a few examples. If the experiment is tossing one coin, your sample space are heads or tails. Rolling a die, the sides 1 through 6. Answering a multiple choice question, maybe the choices are A, B, C, or D. And then tossing 2 coins, your sample space would be heads, 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 tails, tails, heads, tails, tails. So we're going to see a few more examples, but we often list every option out when we write down the sample space because then that helps us figure out theoretical probabilities. So here is what I was talking about. So here's the sample space for rolling 2 die. They each have 6 sides. And this is one way to write it down, the sample space, write down the sample space so that you have every option listed and you don't forget any. So sometimes it can be confusing, or there can be a lot of choices, a lot of possible outcomes or events. So writing it out in an organized manner is helpful to figure out the theoretical probabilities for an event. So as you can see, it's like 1, 1. So both die you land on 1 when you roll them, or 1, 2, 1, 3, 1, 4, etc. And so those are all the possible outcomes in this sample space. Here's another example. So a standard deck has 52 cards. There are 4 suits. It's right there in front of me. There's 4 suits: the hearts, the diamonds, the clubs, and the spades. And in each suit, there are 13 cards, ace through king. And so there's 52 outcomes. If you were going to pick one card, there would be 52 possibilities. So to calculate the event, the probability of an event A, when all outcomes are equally likely, we count the number of outcomes for event A and divide by the total of outcomes, number of outcomes in the sample space. So examples are, again, if you toss a fair coin twice in a row, the sample space, as we saw before, was heads, heads, tails, heads, heads, tails, and tails, tails. So the sample space has 4 outcomes. If we're going to let A be the event of getting 1 tail, then there are 2 outcomes that meet that condition, head, tail, or tail, head. So our probability of event A is 2 out of 4, or 0.5. So sometimes we keep our fractions unreduced, unsimplified, so we can see the total number of favorable outcomes divided by the total number of outcomes. Or sometimes we reduce it, and sometimes we write it as a decimal. And if we roll 1 fair 6-sided die, the sample space is the numbers 1 through 6. If we let event E be rolling a number that is at least 5, then there are 2 outcomes in this event E, 5 and 6. So our probability of event E, or P of E, equals 2/6, or 1/3 of the time. So 1/3 is the reduced fraction. It'd be 0.3 repeating if we wrote it as a decimal. So the law of large numbers states that as the number of repetitions of an experiment is increased, the experimental probability tends to become closer and closer to the theoretical probability. So experimental probability is the probability you get when you actually do an experiment. So if I roll a die, this is going to talk about it, you might not get 2 out of 6. You might not get, the 5 and the 6 every single time, or 2 out of 6 times. But if you roll it enough times, a very large number of times, that experimental probability, what you actually get when you do the experiment, is going to get closer and closer to the theoretical probability of exactly 2/6. So the long-term relative frequency of obtaining the results would approach the theoretical probability of 2/6 as the number of repetitions of repeating the experiment grows larger and larger. So in many situations, the outcomes are not equally likely. A coin or die may be unfair or biased. And so the spots on a die, like if you have if you have a biased die, unfair die, the spots on each face usually are, I'm going to move my face out of here. The spots on each face of the die are little small holes carved out and then painted to make them, easy to see. So sometimes it's possible that the outcomes are affected by the slight weight differences between 1 hole being carved out or 6 holes being carved out. And gambling casino dice are made differently to eliminate that bias. So your standard die you might have at home might be a little bit biased. The ones they make for casinos are supposed to be made to eliminate that bias. They have flat faces where the holes are completely filled with paint that has the same density as the material that the dice are made out of. So each face is equally likely to occur. Otherwise, it wouldn't be fair. So we have or events and events. So an outcome is in the event A or B if an outcome is in A, or is in B, or is in both A and B. So an example of this is if we let that event A be the numbers 1, 2, 3, 4, and 5, and the event B be the numbers 4, 5, 6, 7, 8, then A or B is going to be the numbers 1, 2, 3, 4, 5, 6, 7, 8. So it's all the numbers that are in A or B or both. But we do not write numbers 4 and 5 twice. We don't write things that happen in both A and B twice. We only list them one time. So an outcome is in the event A and B if the outcome is in both A and B at the same time. So if we let A and B be as before, then the event A and B is only going to consist of the numbers 4 and 5 because those are the only two numbers that are in A and in B. So the complement of event A is noted as A apostrophe, but we say A prime, and that consists of all the outcomes that are not in event A. So they're like opposites of each other. So the probability of event A and plus the probability of the complement of A always equals 1 because whatever it was for A, it's going to be 1 minus that because it's everything else that isn't in A. And so an example, so if S is the event 1, 2, 3, 4, 5, 6, and A is 1, 2, 3, 4. So sorry, S was the sample space 1 through 6, and A is the event 1 through 4. Then the complement of A prime, are the numbers 5 and 6. Everything from the sample space S that are not in the event A. The probability of A are 4 out of 6. The probability of A prime or A complement is 2 out of 6. And if you add 4, 6 plus 2, 6, you get 1. One thing also to know about or and events, ors tend to have more things in them because you're putting two events together maybe or multiple events together, whereas A and B events tend to be smaller because you're just taking what overlaps with them. So conditional probability, the conditional probability of A given B is written as probability P parentheses A with this line B, and we reread that as the probability of A given B. And that's the probability that event A will occur given that the event B has already occurred. A conditional reduces our sample space. We calculate the probability of A from the reduced sample space B, and the formula to calculate the probability of A given B is this. So we have the probability of A and B divided by the probability of B, as long as the probability of B is greater than 0, because you can't divide by 0. So an example of this is if we toss one fair 6-sided die, we have that sample space 1 through 6. And if we let the event A be that we roll a 2 or a 3, and B be that the roll is even, so that would be a 2, 4, or 6. To calculate the probability of A, 2 or a 3, given the roll is even, B, we count the number of outcomes, 2 or 3, in that new sample space, B, which was 2, 4, 6. We then divide that by the number of outcomes in B. So that's one way to do it, or if you use the formula, it looks like this. The ones that are in A and B, so that would be 1 out of 6, over the number that are in B, so 3 out of 6, which reduces to 1/3. So the first one written in the words, that's sort of like figuring out what's just in A, reducing the sample space from B, so only taking A out of B. And then the formula is using the A and B over, you don't do it the same way, but that you get the same answer. So one more example, if our sample space is all the ordered pairs of two whole numbers, the first from 1 to 3 and the second from 1 to 4. So an example would be like 1, 4, because you're picking from 1 to 3 first and then from 1 to 4 second. What is S? That's going to be our sample space. And then we're going to go through, we're going to list event A, the sum is even, and B, the event B is the first number is prime. So we're going to list the outcomes in A and B. We're going to do the probabilities of A and B, A or B, what's in those events, and then the probabilities of them, what's in the complement of A, and the probability of the complement of A. We're going to add them together and then do the two conditionals both ways. So what is in our our sample space S? Oh, and the question too, are the two conditional probabilities equal? So our sample space, because we're picking one number from 1 to 3 and then one number from 1 to 4, are the ordered pairs 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, and 3, 1, 3, 2, 3, 3, and 3, 4. So again, A is the event that the sum is even, and B is the event that the first number is prime. So A is going to consist of the pairs 1, 1, because that adds up to 2, 1, 3, 4, 2, 2, 2, 4, 3, 1, and 3, 3. And B, so the first number is prime, is going to be 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, and 3, 4. 1 is not considered a prime number. So the probability of A, if you see how many events are in A, how many outcomes, 1, 2, 3, 4, 5, 6. There's 6 out of the total 12 outcomes in our sample space. So the probability is 6 over 12, or 1/2, or 0.5. For B, we have 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 8 out of 12, which reduces to 2/3, or 0.67. Now, what's in the event A and B? So that has to be in A and in B. That's the outcomes 2, 2, 2, 4, 3, 1, and 3, 3. And this is where it really helps to have those outcomes, those events listed out so you can see what's in both. And then A or B, so that's everything in A or in B or in both. So it's going to be 1, 1, 1, 3, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, and 3, 4. And then the probability of A and B. So A and B had 4 events out of the total 12. So that reduces to 1/3, or 0.33. A or B had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 12. So the probability is 10/12, which reduces to 5, 6, or is 0.83. So what is the complement of A? So it's everything in our sample space S that's not in A. So here was S, here is A. So we're going to have everything that's not in A. So it's going to be 1, 2, 1, 4, 2, 1, 2, 3, 3, 2, and 3, 4. What's the probability of that? 2 ways to think about it. Count what you have in the complement. 1, 2, 3, 4, 5, 6. 6 out of 12. It's going to be 1/2, or 1 minus our probability of A, because the probability of A plus the probability of A prime has to equal 1. So that's what I just did here. So 1/2 plus 1/2 is 1. And now we get to our conditionals. What is the probability of A given B already happened? So we look at B. This is our new sample space, and we can count how many how many outcomes in A exist in B, and that'll be our new probability. Or we can use the formula with the probability of A and B divided by the probability of B. So whichever way you prefer to do it, sometimes it depends on what information you have. Here we've listed out all our probabilities, so using the formula wouldn't be difficult. We also have the sample spaces and the events listed out, so we can do it that way as well. So the probability of A given B is going to be 4/12, so that's the probability of A and B, divided by the probability of B, which is 8/12. So 4/12 over 8/12 reduces to 4 over 8, or 1/2, so 0.5. Now, if we think about it the other way, what's the probability that the first number is prime, B, given A, that the sum was even? So now this is what we're thinking about. This is our new bottom denominator for the formula. So either look in A and pull out just the first number is prime options. That would not be the ones. These would be these 4 here. Or we'll do the formula, which will be A and B, but now divided by the probability of A, because that's the second thing written in the conditional. So 4 out of 12, that's A and B, divided by the probability of A, which is 6/12. That reduces to 4/6, which is 2/3. So those two probabilities, those two conditionals, are often not the same. Something to keep in mind. Occasionally they are, they'd be, but often they're not. So we're going to do one more like that, just because I think these ideas are a little bit tricky and I want to make sure that you feel pretty confident and comfortable with them. But this is example 3.2 from the book, and we have a fair 6-sided die. We're going to describe the sample space of rolling it. We're going to identify each of the following events with a subset of S, and compute the probability. An outcome is the number of dots that show up. So what is our sample space? Then we're going to let A, the event A equal the outcome is even, and event B be the outcome is less than 4. And we're going to do the same thing. What's in A, what's in B, probability of A, probability of B, what's in A and B, what's in A or B, their probabilities, what's in the complement of A, its probability, and then add them together, and then the two conditionals. So if we roll a die, our sample space consists of when we roll one die, sample space consists of the numbers 1 through 6. So what is A going to be in the A? The outcome is even, so it would be 2, 4, or 6. B, the outcome is less than 4. So less than 4, make sure you read these problems carefully. So that's going to be 1, 2, and 3. What's the probability of A? Well, there are 3 outcomes in A divided by the 6 outcomes in the sample space. So 3/6 or 1/2 or 0.05. And the probability of B is the same, right? There's still 3 outcomes in B divided by the 6 from the sample space. So 1/2 or 0.5. Now what's in A and B? So that has to be in both. Well, 2, 4, 6 and 1, 2, 3. So it's just the number 2. But in A or B, it's going to be in A or B or both. So it'll be 1, 2, 3, 4, 6. We're not going to repeat the number 2 because it occurs in both. We're only going to list it one time. And so A or B or both. So the probability of A and B, so that's just 1 out of 6. So there's one event, one outcome. I'm sorry, I keep getting those mixed up. That one outcome in the event A and B, so 1 out of 6 or 0.17. And then there's 5 here in A or B. So 5, 6 or 0.83. Now, the complement of A is going to be the outcome is odd. So it's going to be 1, 3, 5, all the things that are not in A. And then the probability of that is also 1/2. So this time, I think it was the same last time. So we had 1/2 plus 1/2 equals 1. They're not always going to be 1/2, but they will always add to 1. The probability of an event plus the probability of its complement will always add to 1. And so here we are with our conditionals. What is the probability that the outcome is even given the outcome is less than 4? So if we take this as our new sample space, what is the probability that that the outcome we pick is even? Well, it's only 2, so one event, one outcome out of 3. But we can also do the formula, which would be the A and B, 1/6, divided by the probability of B, 3/6, which reduces to 1/3. But again, if we take this as our new sample space and we pick the even outcome, it's also 1/3. So think about which way is easier for you to calculate when you're doing these problems. And then our last conditional, the probability of B, that the outcome is less than 4, given the outcome is even. So we are going to have 2 this time, actually we're just going to have 1 because it's just going to be 2 because we're not including 4 in less than 4. So we're going to have, again, A and B, 1/6, divided by the probability of A this time, 3/6. They just happen to be the same. So we get 1/6. Sorry, we get 1/3. So this time the conditional probabilities were the same, but it's not always the case that that's true. So, what is the probability that the outcome is 7? Well, it's going to be 0 because there is no 7 on a 6-sided die. So that is the end of the video on section 3.1, which was probability terminology, but really was basic ideas in probability.